This presentation is on water use on a farm in Costa Rica. As we know, water is a finite resource, with fresh water being even less available. This project specifically focuses on the wastewater from farms in Costa Rica. It is estimated that only about 3 to 5% of farms treat their wastewater, and only about 79,000 of the 93,000 farms in Costa Rica treat their agricultural waste. The agricultural waste from farms can leak into creeks and streams that run off into the oceans, shown in the image. Nutrients from the animal waste and leaky septic tanks enter the ocean, and if the right conditions occur, massive algae blooms can occur. The massive algae blooms deplete oxygen levels in the water, producing toxins, and end up killing aquatic life. The agricultural wastewater treatment system is composed of digesters, a struvite reactor, and a lagoon system. The goal of this study is to analyze and discuss the economic and environmental impacts of the lagoon system on a small-scale livestock farm in Costa Rica. The scope of this project is to perform a comprehensive life cycle analysis along with a comprehensive economic analysis to determine if this project is viable on a larger scale. With a water treatment system already built, this study will determine if the lagoon portion is economically and environmentally beneficial. The lagoon system is intended to treat water effluent produced by a struvite reactor and digester. The construction of the lagoon system starts with a trough being dug in the ground. The table shows the amount of each item needed for the construction process, including geomembrane, 2-inch PVC pipe, and 4 PVC elbows. The cost of each individual item is included in the table, and each item is categorized in kilogram units. During the operation and maintenance phase, nitrogen and phosphorus are avoided from entering into the natural water systems. From the water treatment process, a product is nitrogen and phosphorus fertilizer. Shown in the table is the market value of both the nitrogen and phosphorus fertilizer. The fertilizer could be used by the farmer or sold on the market. We will use LCA method's recipe for the comprehensive assessment of eutrophication potential and for carbon footprint impacts. The figure shows the carbon equivalents in kilograms from both the inputs and outputs during the construction phase and the operation and maintenance phase of the lagoon. Recipe was used to assess the annual carbon footprint. Avoided products included nitrogen fertilizer and phosphorus fertilizer. This figure shows a network of the construction process. The construction process is the dominant contributing factor when evaluating the annual carbon dioxide. A life cycle analysis using recipe shows that the geomembrane and the 2-inch PVC pipe elbows contribute to the total carbon dioxide. From the construction process, the primary contributor comes from the 2-inch PVC pipe, which accounts for 89.5% of the carbon footprint. A life cycle analysis of the eutrophication potential was conducted using the recipe method. Both the construction phase and the operation and maintenance phase were included in the study. Shown in the figure are the individual inputs and outputs from both phases of the lagoon system. Operations and maintenance is the highest potential to the eutrophication process. Nitrogen and phosphorus fertilizer eutrophication potential outweighs the emitted potential of the construction process substantially. The network configuration in the figure shows the eutrophication potential input from the lagoon operation and maintenance phase. The nitrogen fertilizer avoided is the dominant contributor to the eutrophication process, contributing 69.4% to the total process during the operation and maintenance process. The phosphorus fertilizer avoided contributes 30.6% to the eutrophication potential of the lagoon operations and maintenance.
The present worth benefits were calculated using a lifespan of 20 years and an interest rate of 3%. The present worth benefits came out to $157.55. The present worth cost was calculated using the same lifespan and interest rate and came out to $154.08. The net present worth was calculated to be $3.48.
Some of the positive social implications of this project are that filtered water will assist in irrigating local crops. It will also prevent algae blooms, thus preserving aquatic marine life. By doing this, the fishing industry in the Gulf of Mexico would not be adversely affected. The negative implication would be that the stagnant water would create a potential breeding site for insects such as mosquitoes. Our final recommendations focus on the 3 pillars of sustainability. In the economic analysis, the project is determined to be counterproductive if the interest rate is greater than 3%. In the environmental assessment, the project was determined to be beneficial to the environment due to the containment of excess nutrients. In a social context, the project would ultimately increase quality of life due to the increase in infrastructure, which would encourage ecotourism.